Okay, so at the end of the last video, my 15 minutes were up, and it actually cut me off right in the middle of my thought here. Usually try to keep a closer eye on the timer and end my videos a little more eloquently, but we're just going to have to pick up where we left off. And so we were taking one of our constant acceleration equations, v squared equals v naught plus 2a times change in position. So we want our airplane to get up to 27.8 meters per second. The initial velocity is going to be 0. It's starting from rest. 2 times the acceleration. The plane can accelerate at a maximum rate of 2.00 meters per second squared. And the length of our runway, x minus x naught, I just abbreviated as delta x. So now we can solve this equation for delta x. So delta x is going to be equal to our 27.8 meters per second, and all of that is inside of parentheses and it's being squared, divided by 2 times our acceleration, 2.00 meters per second squared. So when we calculate that all out, we should get 193 meters. Let's take a quick look at our significant figures, as we should do every time. We had 27.8. That's 3 significant figures. Let me go back to the original problem statement here to make sure we've got it right. 27.8. That's 3 significant figures. 2.00 meters per second. That's 3 significant figures. And that's really it, I guess. Those are the only terms we're using in that calculation. So 3 significant figures and 3 significant figures, therefore our answer should have 3 significant figures. So 193 meters is how long the runway needs to be. Now, if you were actually the engineer and you were designing this runway, you probably wouldn't want it to be exactly 193. You would probably want a margin of safety. I don't know what that would be, but you probably round it up to at least 200, I would think, if not more. But the minimum length we need is 193 meters for this plane to be able to take off. Okay. All right, so at this point in the chapter, if you're following along with the book, the author sets forward a bunch of recommendations for solving these problems. A lot of these I've already touched on. So step 1, make sure you read the whole problem, make sure you understand it, read it again. I'll just say that you do need to read the whole problem. Oftentimes there might be a 2-part question. If you only answer one part of it, you're missing out on half of the problem or more. So make sure you're answering everything that the question is asking for. Decide on objects under study and what the time interval is. So it's not often that you're given unnecessary information. Usually the information given in the problem is there for a reason, but you do need to understand what is important, and time interval is a big thing, especially when we get into 2-dimensional motion, but we'll address that a little later on. Draw a diagram and choose coordinate axes. This one I can't emphasize enough. Draw a diagram. When I look at students' homework, I'm amazed whenever I see people who are solving these problems without drawing any pictures. In fact, it makes me a bit suspicious as to whether they're actually solving the problems themselves. I am a very visual person. I definitely need to see a diagram to kind of work out in my mind what is going on, and I would recommend you do the same thing. Now, you don't need to be a Leonardo da Vinci. You don't have to have these amazing drawings. Just simple stick figure diagrams will really help you out, I think, understanding what you're doing and why you're doing it. Write down all of the knowns, and also, importantly, what is unknown? What is it that you're looking for? and then try to understand what physics concepts we've talked about are being applied. More importantly, or more specifically, look at equations. We're going to be given a lot of equations throughout the semester. I have summarized most of them into a sheet that is posted on Blackboard that you can refer to. Choose the one that fits your situation. Usually you can do that by comparing the variables. The ones that are involved in the problem, compare it to the ones that are in the equation, look for the ones that match. And then solve algebraically for the unknown quantities. This is another thing I agree with wholeheartedly. Check to make sure your answer is sensible. So make sure you don't get an answer that just doesn't make sense, that is way out of proportion. Try to estimate in your head approximately what you think the answer should be, and then compare your answer to what you estimated it to be, and see, did it turn out to be pretty close? Does it seem to make sense, or does your answer seem way off? Make sure that before you enter your final answer into Blackboard, that you have verified that you have the correct number of significant figures. Okay, and again, make sure the answer is reasonable, and then check your units. Make sure all the units cancel out. Is a good way to make sure that you were on the right track. Now that's the 9 steps from the book. Here's my own 2 cents. I picked this up a while ago, and it is the guess method when solving a word problem. Write out what is given. Write out what the unknown is. Find the correct equation that you want to use. Substitute the variables into the equation and solve. So we've looked at some problems involving constant acceleration. Now, constant acceleration could be a constantly accelerating airplane or automobile, but a real common situation in which we experience constant acceleration is the acceleration due to gravity. If you take an object and you drop it, it will accelerate downward at a constant rate. And Galileo was the first scientist to prove this, or at least he's very famously associated with this. At the time of Galileo, some people believed that heavier objects fall to the ground faster than lighter weight objects. And basically Galileo proved that that's just simply not the case. Now, I can't mention Galileo without thinking of Bohemian Rhapsody. I don't know if you also think of Bohemian Rhapsody, but I do. All right, moving on. So, like I said, Galileo proved that an object falls at the same rate regardless of its mass. So, the reason why so many people don't believe this at first is because of air resistance. If you take a ball and a sheet of paper and you drop them both, the ball falls to the ground much faster. And so people tend to think that it's because the ball is heavier. It's actually because the piece of paper experiences or is affected more by air resistance because it is so flat. It has such a high ratio of surface area to mass. And so the air molecules slow it down as it falls to the earth. If you were to repeat the same experiment, this time crumple the piece of paper up into a ball so that that large surface area no longer comes into play, then you'll find that the two objects fall to the ground at the same rate. Okay, so it turns out that the acceleration due to gravity, at least the value used in this textbook, is 9.80 meters per second squared. So that means if you were to go to the top of a tower and drop an object off of it, after 1 second, it would be falling at a rate of 9.80 meters per second. Okay, and so the reason why the distance is 4.9 is because if we think about the initial velocity 0 and the velocity after 1 second of 9.8, if we take the average of those two values, we get 4.9. And so that is the average velocity in that interval. And so if we multiply the average velocity by 1 second, we get 4.9 meters. So that's kind of like the average in between. So the average velocity in that first second interval was 4.9. Okay, and then after another second, the velocity will increase or accelerate from 9.8. It'll go up another 9.8. And so after 2 seconds, the velocity is going to be 19.6. And so the average velocity in that 2-second interval is 9.8. But if we multiply that average velocity of 9.8 meters per second by the time interval of 2 seconds, it brings us back to 19.6. So the distance fallen is 19.6. And if we repeat that, it will continue to grow at this exponential rate. So the velocity continues to increase and increase and increase the further it falls. In theory, if there was no air resistance, it would just continue to accelerate infinitely. But of course, there is air resistance, and falling objects do reach what is called a terminal velocity, the point at which the acceleration stops. The velocity remains constant because of the air that is pushing back against that falling object. But that's a discussion for a different chapter, or perhaps even a different course. We are going to make certain allowances for our calculations for free-falling objects, and one of them is that we will neglect the effect of air or wind resistance. Just as a side note, the acceleration due to gravity in English units is 32.2 feet per second squared, but we won't really be using that. And I did mention earlier that the 9.80 meters per second squared is according to this textbook. Some references you might find might have it as 9.81 meters per second squared, but for whatever reason, this particular textbook goes with 9.80. And we'll talk later on how that actually varies slightly depending on where you are in the world. All right, so here's an example problem I came up with here. This is from an actual episode of Top Gear. They dropped a Volkswagen Beetle from a helicopter that was hovering at an elevation of 1 mile straight up. Okay, so it starts at a height of 5,280 feet. If we neglected wind resistance, which is actually considerable in a case like this. So the wind resistance pushing back on a large, well, it's kind of small compared to some other automobiles, but it's still a rather large object, is going to slow it down quite a bit. But if we neglected it, what would its final speed be when it impacts the Earth? So some people say, oh, well, when it hits the ground, its velocity will be 0. Well, that's not really what we mean. We mean like this instant before impact. So how much velocity will it attain if it's dropped from 1 mile up? And as I look down at my timer, I see I'm almost out of time. So we'll actually perform the calculations. We'll do this example problem in the next video.